Bismillahirrahmanirrahim. This is lecture number 19 of the waves in oscillation. Over here we will be discussing about the energy and power of a traveling wave along a stretched string. As a wave passes through a region, it causes to oscillate the particles of the medium, and thus it transports energy. For example, if we hold a stretched string and oscillate it like this one, so by oscillating the string, we work on the string by pushing it up and down, and that work is transported in the form of energy through the string in the shape of a wave. So this wave carries energy in the form of kinetic energy as well as potential energy. So let us focus on a very small element of a string. As shown over here, the element A and element B. As I said, the energy is carried in the form of kinetic energy and potential energy. So let us discuss them number by number. The first, the kinetic energy. Consider a string element of mass dm which is oscillating in a transverse way in a simple harmonic motion when the wave passes through the string. This element will have kinetic energy due to its transverse motion, that is the transverse velocity u. When the element is rushing through the equilibrium position, this one, the y is equal to 0, it has maximum speed and thus has maximum kinetic energy. And when this element reaches its extreme displacement, either on plus ym as represented by denoted by A over here, or at this end, so at this extreme point the particles of the string stops and starts to move in the opposite direction. That is, this element has reached to the top and now it will start moving down. So reversing the direction, it stops, and at this position its transverse velocity is 0. So at the position A, the element will have no kinetic energy and will have maximum kinetic energy as it passes through the equilibrium position. Now we come to the elastic potential energy. As we know, when a wave passes through a stretched string, so the string would have some tension, and due to the tension, some portions of the string are stretched more than the other portions. For example, the string element at position B, or the string element B, is much stretched as compared to the string element A. So this element would have more elastic potential energy than this element. To send sinusoidal wave along a straight string, the wave must necessarily stretch the string. As the string element of length dx oscillates transversely, its length must increase and decrease in a periodic way. If the string element is to fit the sinusoidal waveform, elastic potential energy is associated with these length changes, just as for a spring. When the string element is at the extreme position, that is y is equal to ym, its length has its normal unstretched value dx. This element will have unstretched value dx, while this element is much more stretched at zero position, so it has maximum stretching. So at this position the elastic potential energy is maximum, while at this position the elastic potential energy is zero. The oscillating string element thus has both its maximum kinetic energy and maximum elastic potential energy at the equilibrium position y is equal to 0. While the regions of maximum displacement would have zero energy. As the wave travels along the string, forces due to the tension in the string continuously do work to transfer energy from the regions with higher energy to the regions with no energy. So let us consider that we set up a wave on a stretched string along a horizontal axis, that is the x-axis, as shown over here or over here. We might send a wave along the string by continuously oscillating one end of the string. So in doing so, we continuously provide energy for the motion of the string and stretching it. As the string sections oscillate perpendicularly to the x-axis, they have kinetic energy as well as elastic potential energy. As the wave moves into sections that were previously at rest, energy is transferred into those new sections. Thus, we say that the wave transports the energy along the string. For example, this is if this string is in the relaxed position. At this position, we start to move it up and down. So the regions, as we move it up and then down, so this pulse is created and this is moving forward, and with no energy regions, it transfers energy to those regions. So in order to find the rate of energy transmission or the power transmitted by a wave, so we have to consider both the kinetic energy and the potential energy. It means that how much kinetic energy the wave transports, how much potential energy the wave transports, and in how much time this energy is transported. So if we find the total energy and then divide it by the time during which it is transported, this will give us the power of the wave. So let us first calculate the kinetic energy in a small element dx of length dx and which has a mass dm. So if we consider the element as we have shown, this is, let us consider this element of length dx and mass dm. So the energy associated with this element is let dk, and this dk is half dm into u square, because the transverse velocity of this element is u. So as we know that kinetic energy is half mv square, so for this particular element we will have half dm into u square. V as the transverse speed of the oscillating string element, and this u is actually the derivative as of the displacement, the y. As we know that the derivative of displacement is known as velocity, so the transverse displacement is denoted by y, which we have already taken to be represented by a sine or cosine function. In this case, our y of xt is equal to ym sine of kx minus omega t. So to find the transverse velocity, u will be equal to curly y over curly t, and that is the time derivative of the y. Y is equal to ym sine of kx minus omega t. So if we differentiate it, this will give you ym as it is constant will be out. Cos of the derivative of the sine is cos, so cos of kx minus omega t into minus omega, so minus omega ym cos of kx minus omega t is equal to u, the transverse velocity. Now using this value of the transverse velocity in this equation, then dk is equal to half dm into minus omega ym cos kx minus omega t whole square, and replacing dm by its equivalent mu dx. Dx is the length of the element and mu is the linear mass density of the element. So doing so, we get this relation that dk is equal to half mu dx for the dm, and minus omega ym cos of kx minus omega t whole square, so that gives you minus omega ym whole square into cos square kx minus omega t. This is the kinetic energy. If we divide it by dt, if we divide this equation throughout by dt, so this will be dk by dt, this one, and this dk by dt is the rate at which the kinetic energy is transported, and will be equal to half this thing mu dx divided by dt, because the rest of the things are constant. So we will have dx by dt, and that dx by dt is actually v, the speed of the wave, into omega square ym square, and this is cos square kx minus omega t. Now, how to find the average value of dk by dt over a period, or over one period, two periods, or any number of periods and any number of wavelengths. So we take the average of dk by dt, and that is equal to half mu v into omega square ym square, and average of cos square kx minus omega t. This average of cos square kx minus omega t gives you 1 over 2. So that 1 over 2 multiplied by this 1 over 2 is equal to 1 over 4 into mu v omega square by m square. I will show at the end of the lecture that how cos square kx minus omega t average is equal to 1 over 2. So this is the story, this is the relation for the rate of transport of kinetic energy. Similarly, we have the same amount of potential energy, as we know from the simple harmonic oscillator equation, that half of the energy at any instant, not half exactly, but partially the energy is kinetic and partially potential. So the the potential energy is also equal to the same value, or the average power due to the potential energy is also the same, that is 1 over 4 mu v omega square by m square. So just to find the total rate of energy transmission, we take P average is equal to twice dk by dt average. These two terms come out due to the potential energy. So the average power transmitted is thus given by half mu v omega square by m square, where here we see that the power or energy transported by the wave, by the transverse wave, is proportional to the square of the amplitude and the square of the frequency. Also it is directly proportional to the wave of the speed. But this relation, this is omega square, and the proportionality of P to ym square and omega square is a general result. This is true for all types of waves. Now let us discuss a sample problem on this topic. Consider a string has a linear mass density like this, 525 gram per meter, and tension tau is equal to 45 Newton. You can represent this tension by tau, by T, or by F. Actually it is the force. So you have not to mix it or confuse it with the time period. Here it is clearly mentioned that this is the tension and it is 45 Newton. We sent a sinusoidal wave with frequency 120 Hz and amplitude Ym is equal to 8.5 millimeter along the string. At what average rate does the wave transport the energy? So simply we have to use the above equation, that is P average is equal to half mu v omega square by m square. That is, we have to use this equation to calculate the average power. Now in this relation we see that mu is given, v that is not given over here, omega is not given but it is AZ, 2 phi f is equal to omega and f is given, so it is AZ. Ym, the amplitude is 8.5 millimeter, it is easy to plug in. But what is V? So we know that V is equal to tau over mu under the root, that is the tension in the string divided by its linear mass density under the root. This gives you the phase speed of the wave. So determine omega and V, plug in the values in this equation, and you get the average power to be about 100 watt. Remember that always use the value of omega in radians per second. When you multiply F with 2 pi, so then you don't have hertz per second, rather you have radians per second. Now let us show that the average value of the cos square kx minus omega t is equal to 1 over 2. So integrate it over one time period, you can integrate it over 2 time periods, and then take the average. If I integrate this relation with respect to t and integrating it from 0 to 1 time period t, then I have to divide it by that much amount, that is divided by t, and the final result to average it. So first find this integral and then divide it by t. You will find the average value of cos square kx minus omega t. So whenever you have cos square or sine square in an integral, so break it to a single power, that is use the angle identity 1 plus 2 cos kx minus omega t divided by 2 into dt. Now there are two terms, the 1 over 2 dt and plus the cos kx minus omega t, this term. So the last term comes out to be 0 over any integer number of wavelengths and over any number of time periods. Over here we mention the number of wavelengths because x is over here, x is a variable over here, so we have to replace it by its equivalent constant value, because we are integrating with respect to t only, so x will be considered as constant, but we have to consider the average over any integral number of wavelengths, that is x is equal to 1 wavelength, 2 wavelength, 3 wavelength, and so on. And similarly the time t should be constant as 1t, 2t, or any number of time periods. So over here we are just taking one time period time. So 0 to t cos of kx minus omega t. The derivative of cos is sine, so this is sine of kx minus omega t, but as I told you, you have to specify x, so I put a value of 1 wavelength in the x, minus omega t divided by minus omega, and from I could not find the limit bar, so just I will tell you that this is the limit from 0 to t is equal to 0, because if you put t in this, so omega is 2 pi by t, t is cancelled with t, and you are getting 2 pi in the last one. Similarly 2 pi by lambda is k, and over here you will get 2 pi minus 2 pi sine of 0, so this term goes to be 0. So thus the integral, this one is equal to 1 over 2, and if you integrate this term, this is very easy, 1 over 2 is constant, and dt, if you integrate, this will give you t. So this is t plus 0 is equal to 1 over 2t. To average it, just divide it by t, by the time over which you have integrated it. So 1 over t into this is equal to 1 over 2.